I thought we just started.
3 questions.
It's the first week of it. No.
All right. Yep. It definitely will.
Because I really need the books.
Well, if you, I don't think that's a function of the test being nice. Just
Slightly.
ever so slightly. All right. So all right. So I want to talk about Newton's law of cooling, and this is a very specific differential equation, and some of you who did the murder problem already have seen it in one form. And Newton's law of cooling basically says that the rate is proportional to the difference between the object's temperature and the temperature of the surroundings. So in this case, T is called the ambient temperature. And that's something that's going to be given to you. And it's the temperature of the surroundings. So like you can imagine like if it's a murder and the body is found in a 60-degree room, you can tell how fast the body was cooling because you know that the body was originally at around 98 degrees and the room is at 60 degrees, so the body is going to tend toward that 60 degrees. It's analogous to putting a can of soda in the refrigerator. When you put the can of soda in the refrigerator, it's actually going to end up, instead of, it's going to end up cooling to the temperature of the refrigerator. What else is it sort of? It's analogous to putting a potato in an oven. All right, the oven has a temperature, and the potato is going to tend toward that temperature. All right.
Anything in the oven, right?
No, it has to be a potato. Other things act totally differently. Yeah, they don't. They get colder in the oven.
In Spanish, environment is medio ambiente.
All right, great. So this is Newton's law of cooling. Now, sometimes Newton's law of cooling actually specifies a negative sign in front of the K. I was telling the students who were here about 5 or 10 minutes ago, I actually like leaving K as just K and then getting sort of a surprise at the end to see if it's positive or negative. And I like that. That's a nice little reward at the end. There are generally, maybe I should backtrack a little bit. There are generally, there are specifically 2 types of differential equations that are sort of interesting to look at. And one of those, I'm going to take a look, I'm going to use the slope field program. And if you look, this says y equals some k, which I made up, times y minus 20. This actually looks like Newton's law of cooling, right? And then if I go to quit and I go to program, and I run the program, and I don't know, I'll do like 12 by 12 and see how that looks. I get this slope field. That's not a good one. Well, hold on. Well, all right, let me try. Let's see if this is better. All right, I like this one a little bit better. So I'm going to grab that. Let's see. And if you think about this differential equation actually is Newton's law of cooling. You can imagine if you take, if we're putting something in the refrigerator, if we take like a can of soda and put it in the refrigerator, it's going to cool something like that, and that's what that slope field's telling it to do. If you take something maybe that's hotter, like if you take like a bowl of soup and put it in the refrigerator, it's going to start off at a higher temperature, but in the long run, it's going to get closer and closer to the refrigerator's temperature, and we call this equilibrium.
Oh. I have a question. You know how you set your refrigerator at a different time?
Temperatures?
Yeah.
Yeah.
Why do you touch it? Like, why don't you just leave it?
Some people like really cold milk. Some people like, I don't know.
I thought there was
Like my milk too cold.
What happens if you put a bowl of ice cream into the refrigerator?
Melt.
It gets
It gets
Soggy.
liquid.
it gets warmer, and it actually, in this case, warms up to the temperature.
It does. It gets
So basically, I just want to like convince you that when we have Newton's law of cooling, it doesn't matter the temperature that it initially starts off with, it's going to tend toward equilibrium. And we call this a stable solution. A stable solution is one that tends toward equilibrium. There are actually other differential equations that we'd say are unstable and that they tend away from equilibrium. And you can imagine sort of something like this. These would all be tending away from this equilibrium. And can you imagine putting money in a bank?
Yes.
When you put money in the bank, it's going to grow and grow and grow further and further away from that initial amount that you put in, right? It's going to increase, and we would call that an unstable differential equation, or one that tends away from equilibrium. You could also imagine...
Same thing if you lose money.
Right, so you can imagine buying a car, and as soon as you buy the car, it's going to depreciate. So it's going to tend away from equilibrium again, okay?
So how do you go out?
And certainly, if you think about this as being the interest, right, the percent interest, the higher the percentage, the faster it grows. The lower percentage, the faster you lose it. If your interest rate, actually, you know what? I should have put the x-axis there. If the interest rate is 0, how does your money grow?
It doesn't.
It doesn't. As a matter of fact, it just stays at equilibrium.
Can the refrigerator ever stay at equilibrium?
Yeah, you put a like 40-degree object into a 40-degree refrigerator, it just stays right along there.
40 degrees to begin with.
You brought it in from outside.
When it's 40 degrees.
Exactly. You're killing me. Absolutely killing me. All right. So back to Newton's law of cooling.
We're so close. Why do we always
Look how delicious we are.
Because this is freaking thing right here. I didn't realize that.
Easy, easy. You know, oh yeah, Tori reminded me of this.
Newton has a law of cooling. It doesn't need enough laws. He needs a law of cooling. Really? It needs to be his. When things get cold, he needs to show.
Are you recording this by any chance?
Yes.
No pun intended. You said he needs to know. I said no pun intended.
None whatsoever.
All right.
Yeah, exactly.
Ew. Just a filter, as Mr. Waring would say.
This is the
Least helpful ever. She has like the slowest.
All right. So here it is. Let's see. Shelley, read for us.
Newton's law of cooling states that the rate at which an object's temperature is changing is proportional to the difference between its temperature and the temperature of the surrounding medium.
All right. So I'll get there.
And medium.
It's
Um,
equal.
So here's the thing. The important pieces are the rate at which the object's temperature is changing. So this is the derivative, right? Is proportional. That's our K value. And then the difference between the temperature and the temperature of the surrounding medium. And so you can actually read the problem and say, oh, it's Newton's law of cooling, or you can know Newton's law of cooling. It's a good one to know, Jack. I would know it, right? Yeah, write it down. It's good for you. And there are going to be some times where they might just say, follows Newton's law of cooling, and you have to know, go back and reference it and know what it is. All right. So hopefully they give us at least something like what the ambient temperature is or the temperature of the surroundings. So I have to read a little bit more. Keep going, Shelley.
Hard-boiled egg at 98 degrees Celsius is put in a pan under 18 degrees Celsius running water to cool.
All right. So given that sentence, What's the T? What is the ambient temperature? Are people all right with that?
Just ask for a slice of pizza. Oh, never mind. It's not pizza. Pizza has pizza. It's Passover.
Although I think Sun Valley Pizza makes matzah pizza. Like pizza with I think they make it with matzah meal.
Where's Sun Valley Pizza?
It's in Narber. Oh, there's one, and I'm sure there's a...
Oh, the joys of...
Alright, fine, Wynwood. I feel like it's close to Narber.
Yeah.
I'm thinking the one on Montgomery.
Yeah.
Yeah, okay, fine.
Like,
Yeah.
Sam's?
No,
No, that's not where I'm thinking. Desiree.
Okay, could you really quickly explain why we use chose 18?
Because we're going to put the egg under the water, and the water is not going to change temperature. The water is coming out of that faucet is going to stay 18 degrees. The egg is going to end up changing temperature. Okay?
Like the 18
So-
is like the refrigerator.
Yep.
It's going to take a
So-
while for it to reach 20 degrees Celsius.
Well, let's see. All right, so I now need to solve this. It's a differential equation, first step.
Hit those on the things together.
So DH
Get H and T together.
minus T or 1 over T equals KT.
And the integral sign in front of both.
We're not doing
Ln of h minus 18 plus c1 equals kt plus. So you have to do most of them.
So H minus 18 is equal to, I'm actually going to say C e to the kt, and I'm going to get rid of the absolute value signs and make that C e to the kt all at once. And so we end up with H is equal to C e to the kt plus 18. I now need some information to find C and find T. Read that second sentence again, Shelley.
A hard-boiled egg at 98 degrees Celsius.
All right, that's some important
That's the
information.
K. No, that's the H.
initial H.
Right, that's the
All right, now wait, you said two different things. You said that's your initial H and that's your C.
It's not
Okay.
Usually T is initial.
because that's what's changing.
So we know that 98 equals C e to the k times 0 plus 18. E to the 0 is 1, so C plus 18 equals 98, or C equals 80. That's important. In this case, C is not your initial condition. It contributes to what the initial condition is, but the equation is H is equal to 80 e to the kt plus 18. And I think I need to do a little bit more work to find out what K is. E to the...
After 5 minutes, the egg temperature is around 38 degrees Celsius.
All right, let's do a little
I have
algebra.
a question.
Hold on.
0.
Mike,
That 38, it is right.
That should be a T.
Algebra.
on K. That should be a T on K.
First step.
Oh, it's like,
Subtract.
Yeah, right here.
Right where are you?
Subtract.
Yeah, okay.
that was 50.
All right, 20. Jack, next step.
Divide by 80.
Julia, next step. Chris.
Divide by 5.
Okay, so we found out what K is, and if you have your calculator, and my little reward, I'm happy because
It's negative.
K's negative, so I'm cooling.
What's
Yeah.
the positive?
If it was positive, to me that would mean it's increasing, it's getting bigger. This is good because it's negative.
Weird.
No, this is great. The temperatures.
If it was positive.
Oh,
Wrong.
I guess that's a good point. Like, you could actually tell from your K value whether you messed something up algebraically or not. I never thought about it that way. You're right. It's a good check.
We got it right. We got everything right except for the
All right.
Was that because you did it?
Yeah.
In my hair?